what we're going to talk about today is called confidence intervals. And I thought I should do this today because it ties into what it is that we're trying to do here. So I'm going to talk for a minute, but make sure that I get back to the idea of levels of significance, okay? So here's where we're at. We're going to actually pivot in this class. All up until this point, what I've done is give you the theory behind what it is that we're doing with the math, right? Because the math isn't hard. Addition, subtraction, division. Maybe you got to turn your phone sideways to get the little square root box, but pretty much the math is not hard. Understanding what number goes where and which equation to use, that could be a little bit difficult. But what we've been able to do so far is just learn the math. Now we got to learn what to do with it. And that step requires us applying probability theory. So when we start talking about curves and the area under the curve, area is a somewhat tangible thing, right? If I held up two phones, I got my phone. Anybody have a phone I can borrow? You've got one. Okay. So I have two phones in my hand. Which one is bigger? Why? You think mine's bigger? How do you know? You're looking at it, right? The area of the phone is bigger. Is there any way that I could test that? I like Nick's idea. What you're talking about is volume, right? The eureka moment, the volume of something, by measuring not the thing but the displaced water by putting it in the tub. No, I'm not putting my phone in a tub. I paid a penny for it on Amazon. All right. So we could look at, and what Nick says is put them on top of each other. And it's clear that my phone is bigger than her phone because you can still see mine behind hers. Right? That's area, right? This consumes less area than this. Now, you're talking about volume, which one's thinner? Mine's thinner.
No, it's the same thing, really. Just bigger.
Yeah, okay. That's tangible. And in this class, when we draw the curve and we talk about the area under the curve, you can see that area, right? You can see that whether or not this little slice is smaller than almost all of the curve, right? So area is generally something that's tangible that we can see, whether it's how big of a car we have, how big of a house we buy, how big of our screen we have, right? I got a 60-inch flat screen. That's area. We deal with that all the time. It turns out that the math for computing area under the curve is the exact same math to talk about probability, because the probability of an event happening is always between 0 and 1. So what we did is we made that step. In order to do that, though, we got to keep making more and more little steps so that we can understand what it is that we're doing. So here's where I think we're at in the course. We've talked about the idea of data. We've talked about how we can collect it. We've also talked about the difference between a sample and a population. It's always sort of been looming around, right? We have to make inferences. Well, what we're doing, and the reason that we need to make the turn with the math, is to say we have a sample, but we want to make guesses about the population. All right? We need to make this inference so that we can, get in the back. We need to make this inference so that we can take meaning from the sample that we have. The best example of this in the political, social context of this class is polling. Anybody watch the debate the other night? Who won the debate? It does depend who you ask. That's called polling. So if we were to poll a large number of people, according to CNN, who did the polling, what did CNN decide? Hillary won the debate. Does anybody remember the numbers from the debate that CNN had? I think it was 53-39. Wasn't that's about right. Yeah, low 50s to high 30s. Okay. According to CNN sample, 53% said Clinton won the debate, and 39% said Trump. Okay. Why is that of interest to anybody? Well, there are some political scientists that study the effect of presidential campaign events like debates, and they want to know if it has an impact on people's votes. Well, we can't go out and ask every individual that lives in the United States, who do you think won the debate? It would take forever. It would take months. And you know what probably the most popular response would be? What debate? Okay. So what CNN has to do in order to get you to keep watching CNN is offer you some information about the debate. Right? So have this thing where you watch the debate, it gets over at about 10:30, and then you're like, oh, I can go to bed now. No, you can't, because you got to sit up and watch everybody talk about the debate that you just watched to see if they saw the same thing that you did. And Trump's people never saw the same thing that anybody else did. But the CNN guys are really good about going, huh? Okay, let's treat you like you have an idea. So we stay up and we watch, and we get the analysis, and we understand, all right, this is the line that we're going to talk about. We're political people mostly, if you're in this class at least. So CNN's value added is that they do a poll of debate watchers. Now, they didn't call you. You watched the debate. They didn't call you and ask you who won. Did they, Jake? Okay. So they've got a sample. But they're going to use that sample to tell us who won the debate, right? Period. In the United States, who won the debate? Clinton won the debate. They can do this because they've made the next step with the math that we've learned. And so today's step is confidence intervals. Confidence intervals are another way in which we can explain the probability of an event happening. And we can do that using a sample that we have. So when CNN tells us that 53% believe Clinton won the debate, they're comfortable in that because they've collected a sample of people who have watched the debate. They collect a large enough sample, so the N is big enough that they can have a certain amount of confidence. In most cases, it's 95% confidence if we're testing a hypothesis, which leads kind of to where Ryan's question is about this whole idea of rejecting hypotheses. The reason we can do this goes back to that central limit theorem. As N gets bigger, our samples are better predictors of populations. Now, talking about confidence intervals, we're sort of placing a bet. And the bet that we're placing is, to what degree did our sample come from the population? Well, we know it definitely came from the population, but at which degree does it represent the population? And so I'm going to show you sort of the bet that we make so that we can better understand why it's important to have confidence or construct confidence intervals around our samples. Okay. You all done copying the slide? Almost? Here's a website that has a little applet where it's just going to do random samples for us. I'll put a link on Moodle. All right, so what we're going to ask it to do is generate for us a sample mean from a normal distribution, and we're going to do z. We're going to do a z-score. And let's think about, all right, what do we want our sample to look like? Well, I just did the default numbers that we've been using for the IQ, right? IQ, you guys have memorized these to the extent that you're getting homework questions wrong with what the book says. 100 is your mean. It's our average IQ score in the population with a standard deviation of 15. We'll do a sample of 100 people. So let's pretend we have 100 people taking the test. All right. I hit the little sample button. And what it did was it drew a random sample of 100 people using this distribution, right, these figures. And for this one, this is where it is, right? It's about 100. It's probably like 99 for that sample mean. Okay, that's one. One down, 99 to go. It did another random sample, and here we are a little above 100. Here's another sample. This one's red. What happened? Well, this sample came outside of our confidence interval for what we would expect, right? Given this distribution, right? Because we said we want 95% confidence. Why 95? Because we always use 95. This one, whatever this number is, it's outside. Now, I've done this 6 times. And of the 6 times that we've done this, 5 of them have been within that confidence interval. So I'm going to keep hitting the button until I get to 100. What should we expect to see? Well, we should expect to see that in our 100 samples, 95 of them had a sample mean that was within our confidence interval. (97). That's pretty close. We're not going to get an exact number until I keep going 1,000 times or, okay, I'll sit here and hit the button 1,000 times. As I keep doing this, look at this number here. Because this is the percentage, right? At a certain point, what should we see happen? This should get down to 95%. This number down here at the bottom. And once I have a n that's large enough, it won't move from 95%. So now we're down to 96% of the time. Oh, we're climbing up. Oh, we went back down. 96.5, 96.6. Anybody want to take a turn? I'll just switch hands. No, you can't just leave it hitting down. You got to actually hit the button. 97.2, going in the wrong direction. Looking like I don't know what I'm doing. That's okay. I've got a big fancy college word that'll explain away why this isn't working the way it should. Stochastic. Means there's a bit of randomness to how this is going to work. You're going in the wrong direction. Oh, I hit 500 and it's still going. 96. Come on, get down. I'm going to quit when it says 95 point something. And it won't do that. It might not ever do that. I might need to get to like 1 million. I knew you would be good for something someday. And that's the people. That's how I talk about the people I like. All right. All right. And I got to 96. I'm quitting. All right. So we did this draw 683 times. And 662 times, it came out that the number we picked, or the number the computer picked, was within that sample mean. I think my n was too big. I think having 100 people or 100 instances might have been the reason why. So I'm going to go up to 100 and see where I'm at. Ah, better, 96. So why was there more errors in this one? Well, because before I said that we should have 100 people taking the test. This time I said, let's just do 3. Right? Smaller the sample size. We know this by looking at students' t-distribution. What happens? More errors out in the curves, right? So we should get more instances of the wrong, the wrong sample mean. Okay. So that was my fault. I had this n being way too large. Right. With a smaller n, we're going to be closer to that. Ooh, down to 95. There we go. Right? Now we're what we should get. So think of a confidence interval as sort of a bet. I have a sample, whether it's this class's feeling thermometer scores for Hillary Clinton, which were like 32 out of 100. And if I take that sample mean and I use what we know about the area under the normal curve, what is the probability that our sample mean is close to the population mean? Right. We can define how close it is by the confidence interval. Okay? So the confidence interval gives us that idea of closeness. Anybody here like to gamble? Right? What if I told you there was a game in Vegas where you had some information and you played, you won 95% of the time? That would be amazing, right? You drop out of college? I would too. I'd drop out of college. I'd go there and I'd play that game. Because we know in Vegas, what are the best odds you're ever going to get at a game in Vegas? What's that? Like about 49-something%. I have a way that I play roulette where I only lose out of 5 possible numbers of the 36, 38 when you include the zeros. That's the best you can do. That doesn't include like more random chance like cards and how many cards are in a deck, like with 21. That's the best you can do, is to win 33 out of 38 times, which is like 86%. And when I go and I do that, I still lose money.
That's because the amount you net is less than the bet itself.
Yep. So you get wiped out. So you have to make it through like 3 spins of the wheel before you have earned enough money. It's hard. All right. So if there's a game where you can win 95% of the time, whew, right? I have a bad joke about maybe that's the casinos, the game that was in the Trump casinos and why they're all bankrupt, but I need to work on that. All right, work on that joke a little bit. All right, 95% confidence. We can figure out what that range of close is. And we can do that just using our z-scores. This example makes sense, people? You want to watch me hit the button for a little while longer? Yeah? Just sit here and 95.0. And that's when we stop. Okay. Okay. So let's go back to class. So here's our friend, the normal curve. Again, we know this curve intimately. We might not have memorized the equation that will build the curve, because that's got some math that if I showed you, you'd get scared. Natural log, E. What does E stand for? So this is our friend, the normal curve. We know that the normal curve is centered on our mean. It's always centered on the mean. It always has a z-score at the mean of 0. Sorry, 0. Right? We know that we can find where we're at on the curve using a z-score. Z equals x bar minus mu over sigma, and various variations of that, depending upon if it's a sample mean or if it's n is small, we use t instead of z, but let's just stick with what we know. So here's a really simple way when you're asked to compute a confidence interval. What are the steps you're going to do? Right? It's all bucket on the floor for me. What's the process that gives us the result we want? Well, first thing we do, we draw our curve. Okay, I found one so I can not fight with my pen the whole time. What confidence interval do we want to have? What number out of 100 times, if we were to do the sample game where I just sit there and push the button, are we going to get a number that falls, that has the population mean in it, has mu? By default, what number do we want? No. How much confidence do we want to have? We want to have 95%. Right? So 95% of the time, we want our sample to be close to the population mean. Now I've got a percentage, but it's under the curve. So under the curve, it turns into what? It turns into area. So if I want 95% under the curve, and I turn that into an area, how much is left outside of my confidence interval? 0.05. How many tails do I have? Right now I've got 2. Let's just stick with that. Brandon, introduce yourself to the class. Yeah. You showed up. I get to pick on you. Who are you? What are you doing? Where'd you go? Where you work? Okay. And Brandon took the first version of this class 3 years ago. Brandon, am I lying to them when I say that we pretty much use 95% for everything? Not lying. Good. See, you're useful again. Okay. What if I were to say, you know what, I don't need to be 95% confident. I only want to be like 90 confident. Okay. It depends on who you ask, which means there's some... Why? Thank you. Okay? So why do we use 95%? Because we want to be really certain. Now somebody in here is smart. And you're thinking, well, if I can go to Vegas and I can win 95% of the time, what do I really want? I want to be 100%. Okay? So I want to be 100% of the time. So there are some people out there that say, listen, we've got the math for 95. Why don't we go up to 99%? Why not? Okay, go ahead and do it. You can, as a researcher, say, Yeah, I know everybody's at 95% confidence. But what about 99% confidence? There's one more jump up. What about 99.9% confidence? You can do that. Right? You can do that. But let's think about it. What is that going to do to our confidence interval? Because our confidence interval reflects the amount of the curve that we take up. So what's going to happen to those little lines at the bottom where I'm marking out my 95%? Where's my 99% going to be? Way where? Yeah, it's going to be way down in the tail if I want 99%. And where is 99.9% going to be? It's going to be off the screen, right? It's going to be way out here. So what happens to the size of my confidence interval at 99.9%? What does it effectively turn into if we're guessing a number? If we're going back to the IQ example, if we're guessing a number between, we're guessing a score, and we want 99.9% confidence. Look at the size of this band around the estimate. Are there any scores that are outside of the 99.9% confidence interval? Maybe. Let me know if I ever get one. I'll even make it harder. I should make it easier. Let's say an n of 2. Let's keep going. Oh, I got 1 on the first try. Stochastic, right? Randomness. There's always that chance of what shouldn't happen happens. Whew. Thank God I'm not up there for 3 hours hitting the button. But as I keep going, and this is why I lose money when I go to Vegas. Because you have a plan, and you're like, oh, it's going to work this way. This is what the math says. You hit that 1 in 1,000, but you're like, well, I got 999 to go. Doesn't work that way, right? Probability resets at every spin of the roulette wheel. I got 2. I got a second one. Whew. All right. But we can see, look at, our confidence interval is so big, it actually goes all the way out. It's off the axis of the little chart. So you can be more certain, but at what cost? That you accept a wider range of values. Okay. So when we think about confidence intervals, right, we have to make a decision at what we want our probability to be, what our decision rule is. For you guys, just assume 95%. It is the most common score that we use in social science. You do not have to defend yourself if you use 95%. Everybody's okay with it. Divide that by 2. So we got 0.05 divided by 2, that's 0.025. Look up the z-value. So you get out your chart and you look up for that number in the chart, but we're not going to do that because you all have a midterm on Monday and you have memorized what is the most important z-value that corresponds with a 95% confidence interval? 1.96. So a z-score of 0.95 or whatever, some little note to yourself, is 1.96. So here's what we have. we have a framework for understanding the randomness of a sample. We know out there in the world there are billions of people. In the United States, there's 330-something million people. CNN on election night doesn't have time or your attention span to call all 330 million people. So they have to come up with what is an acceptable sample size for them so that they can give you a number. And they can report that Clinton won the debate. She beat Donald Trump by 14 points. And have that be true. Ish. As if they were gambling in Vegas, right? Because they want to win more than they lose. What happens to CNN's credibility? What will happen to CNN's credibility if on election day Trump wins 80% of the popular vote? It'll be discredited. Because all along they've been telling us at things like the debate, and every few days a new poll comes out, how close is the presidential race? If it comes out that Trump actually had the support of 80% of Americans, everybody's going to go, what were you guys doing when you told us that 53% thing? We'll want to know. And then the next time they tell us a number, we'll go, are you sure about that? There was a famous event in the media regarding a presidential election where they thought they knew who was going to win, and they were wrong. Does anybody remember that? Dewey defeats Truman. Everybody thinks that Dewey's going to win the election. That's right. Truman was not elected. He took over for FDR. He was not a national politician. The first election where he's got to run by himself, he goes up against a popular Republican, not the guy that invented the Dewey Decimal System. Okay, and for the time, so this is 1948. No, yeah, 44, 6, whatever. The polling said Dewey's going to win. You know what polling was in the day that affected how the Dewey defeats Truman thing? It was not phone calls in the 1940s. It wasn't even newspapers. It was something more obscure than that, something your grandparents used. Reader's Digest. There was a publishing company that had magazines like Reader's Digest. Some of you guys don't even know what Reader's Digest is. Next time you're at home at Grandma's house, and she's got, like a bookshelf full of old stuff, there'll be a magazine that's about the size of a giant iPhone. And Reader's Digest was just a book of random stuff that you would read. They'd have jokes in it. They've had stories in it. They'd have selections from fiction. There's a poetry section. It was a magazine that you would read just because you like to read. It wasn't like an Us Weekly or anything like that, but it was just something that you wanted to read. And it was a magazine, so it was disposable, but it was popular. Lots of people had it. My grandma had it. What they did in publications like the Reader's Digest is they put little cards, little postcards in, asking the readers to know who they were going to vote for. So the postcards that they got back were from people who read Reader's Digest. Now, what kind of sample is that? How do we think that sample would skew? It would skew towards people, A, that could read. I'll give you that one. Although literacy is not exactly rare at that time. Why older people, Ryan? Because old people love the Reader's Digest, right? Okay, so it skewed older. It skewed people who had money to waste on something like Reader's Digest. Okay, so it skewed Republican. So when the newspapers are predicting who's going to win, they go, well, we got this poll thing. It's scientific. It's got numbers in it. It says that Dewey's going to win. He's got support from all over the place. These polls never worked. And there's a famous picture of President Truman holding up a newspaper that says Dewey defeats Truman. And Truman's got a big old smile on his face because he knows he just won the election. That was a bad poll because they misunderstood how polling works. They focused on the problem of the sample size. They thought they had a really big sample, but they didn't focus on how that sample was generated. When I've been doing the example with generating a mean, that's completely random, right? The computer is just picking 3 numbers or 2 numbers from all of the possible numbers under that curve. It's just randomly doing it on its own. So when CNN does a poll now, it understands, okay, I got to have a more random sample, and sample size isn't the most important thing. It's most important that it be random. But we also know that as the size of the sample changes, our confidence intervals are going to change. This is the equation that you would use, and you have used, to generate the bounds of a confidence interval. You take your sample mean, and you add and subtract, because you got both sides. You have an upper bound and a lower bound. That z-score is the z-score that you pick. For the most part, it's going to be 1.96. You're going to adjust the z-score by the standard error, which is the standard deviation divided by the square root of the number of observations. Again, this is our old z formula, just solved for something else. So how is this going to work? Well, you're going to generate your sample mean, or you're going to take your sample mean from an existing data source. I'm completely making this up on the fly. Let's see, 53. CNN did their survey. They got a sample mean of Hillary Clinton winning the debate was 53%. 53% said Hillary won. They don't want to get this wrong. They don't want a Dewey defeats Truman situation. So they select a confidence interval. We want to have a good idea about where we're at. So 1.96. N is the number of people they called. I tried to pay attention. One night that they did this, it was 534. And because I'm doing this on the fly, I can't remember what S was. Yeah, but I don't need that for this. And what they calculated was that the confidence interval that they could create from these numbers, and the one that I don't have, they think the mean is 53. They want to know where the upper and lower bounds are. So what was this number here? It was 4.2. I do remember that. So what does that mean for us? Well, given the sample that they have, we are 95% confident that really in the population, the sample mean, or excuse me, the population mean, will be between 48.8% and 57.2%. After CNN's pollster calculates this, they go, all right, does that still mean that Trump won? Or excuse me, that Trump lost and Clinton won? Well, what is the other thing do they have to do? They have to do the same for Trump's number. Okay, so Trump was at 39. 39 plus 4.2 is 43.2. If Trump's best number with 95% confident is 43.2, and Clinton's worst number with 95% confidence is 48.8, should CNN be comfortable predicting that Clinton won the debate? Yeah, right? So even though they have just a sample, because CNN has an understanding of things like the normal curve, the empirical rule, the central limit theorem, how z-scores work, they can make this decision. They can say, we're going to go out and just say Hillary Clinton won this debate. It takes them about, see, the debate ends, it takes them about 45 minutes to finish the poll, run the numbers, and come up with the graphic to put it on. So all these debates that I've been watching, I just wait till about 11:15 and they'll tell me how the public reacted to it. With each debate, Clinton has won every debate according to the CNN poll. This one, I remember that the Trump number was bigger than it was from the first debate. So 39 was actually a really good showing for Donald Trump. I think the first debate, Clinton had like 59% she won. And so with each debate, the number that CNN has said has always been in the 50s. But I think it's gone down a little bit, and Trump's number has gone up a little bit.
I only asked to see if it contradicted like the second one, and like say for instance, like if Trump was 53, Hillary was 39 for the second debate.
No.
Then CNN has no idea what they're talking about according to
No.
cancellation.
From people who have watched all three debates, Clinton has said to have won all three debates, because you have people that are describing Trump's performance as things like, you know, dumpster fire, like dumpster actually on fire. They love to put that little picture up. I read a story about people are wondering, like, where did this expression and picture come from? It's an internet thing. So what the political scientists would explain is that, well, people's expectations of Trump are actually going down. So when his debate performance stays the same, they can say, well, he actually did a little bit better, right? That's the thing that people will caution you about. All right, before you run off, I only got 1 minute. So what's going to happen to our confidence intervals as things change? Well, let's just look at the equation. As the sample mean increases, that means that n number goes up, which means the fraction gets smaller, right? When the denominator gets bigger, the fraction gets smaller, which means our confidence intervals come in. Okay? So that should say sample size. Sorry, sample mean increases. As the sample mean increases, nothing happens. We just change the bounds. As the standard deviation increases, what happens? Well, that's the numerator getting bigger, which means that fraction actually gets bigger, which means our confidence intervals get wider. As we decrease the confidence level, well, that means we're putting more area in the tails if we decrease the confidence level, which means our z-score gets smaller, right? And as we increase sample size, well, that's the one that I already did, right? Sample size is a good thing. It makes our confidence intervals thinner.